That's not the right one either. Whoops. Having a good time now. Oh, there it is. There she be. Thank goodness I can edit these movies. Alright, we're going to try again. So, we're moving into lesson 3, which is all rational functions. So, we're changing gears, we're switching over, but it's not something out of the realm of what we've been doing. By definition, a rational function is a function where you have a variable in the denominator. Okay? So it's written in the form p of x over q of x, where q of x is a function, q, x is the input variable in the denominator. If you take a look here, x is in the denominator. That's what's going to clue you into the fact that you have a rational function. Because of that, we now have domain issues. A variable in the denominator gives you domain issues. What are the 2 rules for domain that you always have to watch out for algebraically? Jordan. The denominator can never take on the value of 0, and under an even root, you have to keep a positive value. Okay. Now, that contradicts a little bit with what we did at the beginning of this unit when we talked about imaginaries, but again, imaginaries are not real. They're their own special set of numbers. But in general, those are the 2 things we have to consider for domain, because when we graph, we don't graph imaginary numbers right now. So if you take a look here, what's the value of x that's going to violate the denominator, hence not included in the domain? 0. If you go into the table, you'll notice that it gives you an error. Okay? So if I look at my picture and I go to where 0 would exist, I now have a horizontal asymptote line. It's a dotted line. Those of you who have 83 calculators, TI-83s, or aren't up to date on programming, you may have a vertical line. Okay? What we do want to recall is the fact that if your calculator gives you this, the heartbeat looking thing, that vertical line is not part of the graph. In the earlier versions of the calculator, they put it in there to be helpful, and it confused students. It's still confusing them for those of you that have those versions of the calculator. This line is actually a dotted line. It is a boundary line between the 2 curves. Okay? So if we move forward, the vocabulary word that I mentioned is the word asymptote. In a rational function, we have vertical asymptotes, which are the values of x that violate the denominator. We also may have a horizontal asymptote. There are 3 rules that determine the horizontal asymptote. Okay, we're going to talk about all of those. Vertical comes from the denominator. Horizontal comes from rules. And today we're going to go over all of those. Alright, so moving forward, I would like you to think of asymptotes like electric fences that keep animals in. We never want to touch them, let alone cross them. There is one exception to that, which we will talk about in a moment. So if you look in your notes, the first thing we're going to talk about are vertical asymptotes and how to find them algebraically. Vertical asymptotes, are found at the zeros of the denominator. Okay? They are what violate the denominator, what are not included in the domain. So if I look here, what values of x can x never ever take on because it will violate the denominator? 2 and negative 2. Okay? 2 and 2 goes here. I'm going to do this. I'm going to cross the equal sign out and make a do not equal sign, because I want to reinforce the fact that the denominator can never ever be 0. So if we determine what gives us the zeros, that tells us what we can never ever use. So x can never ever be plus or minus 2. which means we have a vertical asymptote at positive 2. So the translation of this is that at positive 2, I have a vertical asymptote, and at negative 2, I have a vertical asymptote. Algebraic calculation, translation to the graph. All right, moving on. Moving on up. Horizontal asymptotes. Horizontal asymptotes are determined by comparing the degrees. Okay, so we have a degree of the numerator, we have a degree of the denominator. 3 cases. Take a moment, write them down, and then we'll do some examples. Alright, so here's the short form. If you want to take these maybe in the margin, good idea. The degree of the numerator is less than the denominator. Automatically, y equals 0, which is the x-axis, is going to be your asymptote horizontally. If the numerator is greater than the denominator, there is no horizontal asymptote that exists. And if they are equal, the degrees, we take the ratio of the leading coefficients. So notice x squared is my highest, x squared is my highest. So I take the ratio of that capital A up top over the capital A of the bottom, and I get a numeric fraction out. That's going to be the location of your horizontal asymptote. So those are the short forms of what it says with all of the words. Write down what you need. We're going to do examples to explain them. Does anybody know what the deal is with coffee and when the Eagles win?
They stopped there.
They stopped it. What did it used to be?
If they win, you get free coffee.
Oh. Interesting. Are we okay? Can I move forward? Need a minute yet? 1 minute, 30 seconds. Okie dokie. So here's our first example. 2x plus 1 over x squared minus 4. What's the degree of the numerator? Degree what? 1. Highest power of x is 1. So this is degree 1. What's the denominator? Degree 2. So which rule applies? Top. Numerator is less than denominator, so y equals 0 is my horizontal asymptote. That's what we're comparing. Moving on. You're going to be asked to find the zeros of a rational function. This gets a little confusing because I believe we use the word zeros when we define the vertical asymptotes. But let's go through the thought process again just to reinforce. Vertical asymptotes come from what violate the denominator. Horizontal asymptotes come from comparing the degrees and then applying the correct rule. The zeros of a rational function are going to be where the numerator, which is allowed to equal 0, by the way, is equal to 0. So if I look here, don't get caught up in the algebra. Oh, I see x squared minus 4, that's difference of squares. That's great. That's going to answer the question about vertical asymptotes. I want you now to take the numerator, 2x plus 1, set it equal to 0, and solve, because that x value is allowed to take on a 0. Hence, it's a 0. Okay. So just like earlier in the unit when we said, oh, what's the 0? The only 0 we have is negative 1/2. That's what they're asking using that big word that doesn't look like it should have an E in it, zeros. Oh, Jordan. Oh, Jordan. Just wait. Wait for it. Wait for it. All right. You are also going to be asked the question, what is the domain of a rational function? So we're asking all these different questions about these functions that I'm going to give to you. So the domain is going to be what? Everything except for what x can't be. Where do we determine what x can't be? Connect the dots. Where? Top, bottom, bottom. So when we talk about domain, we're talking about vertical asymptotes, correct? In your head, connect those two ideas. Domain is related to vertical asymptotes. So what x can't be? X can't be what? Plus or minus 2. How do we write that as an interval in domain? X can't be plus or minus 2. So let's go back to our number line. X can't be 2. X can't be negative 2, right? Can it be every other number? How do I write those three intervals? Negative infinity, negative 2. Break in the graph, negative 2 to 2. Break in the graph, 2 to infinity. And those breaks happen to be vertical asymptotes now. Because it's rational. Good? Turn the page. All right, so of course we're going to abbreviate and condense everything. You can do this in your homework as well. Put it all together. I'm going to give you a rational function, and you need to answer these questions appropriately in the correct form. So for example, vertical asymptotes, the first one that we have. Okay? Vertical asymptotes come from what part of the fraction? Denominator. What can x not be? Your thought here is that x cannot be negative 3, correct? Okay, which means in a rational, I have a vertical line. How do I write the equation of a vertical line? So this is what I'm looking at. At negative 3, I have this vertical line. How do I write the equation of that line? Prerequisite unit, x equals -3. Now, I'm writing this on purpose because this is an equation of a line. This is a statement about what value of x you can't have. So if I ask you for what is the vertical asymptote, I want the equation of a line. Where does my horizontal asymptote come from? Three rules, correct? What's the degree of the numerator? Degree 0. Denominator, degree 1. What does it mean if the degree of the numerator is less than the denominator? Y equals 0. Y equals 0. Again, this is an equation of a line. Now, what are my zeros? Where do the zeros come from? No, zeros come from what part of the fraction? The top, right? Do I have any x values going in here? So the answer is none. There are no zeros, which means there are no x-intercepts. None. Okay. Remember, this comes from the numerator. 1 equal to 0 is a false statement. There are no zeros. Now, domain. Where do I look for to determine my domain? Denominator. X cannot be what? So now how do I write that? Negative infinity to negative 3. Union with negative 3 to infinity. Every number in the world except for negative 3. Equation, numbered list, interval notation. That's what I'm looking for. All right, so now let's move over to example 2. Example 2. Vertical asymptotes. Where does it come from? Where? Denominator. Factor the bottom. What do I get? X minus 2 plus 1. So, vertical asymptotes. How many do I have? 2. X equals what? And x equals negative 1. Again, these are equations of lines, vertical lines. Ooh, horizontal asymptote. Sweet. What's the numerator degree? Degree 1 over degree 2. Horizontal asymptote. Y equals 0. Where do my zeros come from? Zeros come from the numerator equal to 0. X equals 0. 0. And domain. Where does domain come from? Bottom. So x can't be what? 2 or negative 1. Picking it up? Seems easy? Feeling good? Feeling bored? You did? Really? You feel bored? Smidgen? Just a little bit bored? Okay. All right, we're going to skip the you try for now. I'm going to ask you this question. Take a look. We're skipping the 2 you try ones. We're moving down to the bottom section. What happens if you factor the top and the bottom and all of a sudden some of those quantities start to cancel? Does it affect your answers? What do? Do you leave them in? Do you cancel them? What do we do? What happens to the graph? Big question mark, yes? Jordan, do you know the answers? No? This is the monkey wrench in the system right here. What happens in this case? So let me give you an example. Take a look at example 5. If I go to example 5 and I factor it, Do you see how I have an x plus 2 in the top and an x plus 2 in the bottom? What happens? Not really sure. Okay? You're going to see in your notes that, I'm going to go back here, any factors that cancel out top and bottom create a hole in the graph. They're not a vertical asymptote, even though you're going to say, well, wait, the denominator, though, it contributes to that. But the fact is they become something special unto themselves. Okay? So there's your definition. We're going to talk about a hole in the graph. So, as you can see in example 5, you want to take your function. You want to factor the top and you want to factor the bottom. Now, I'm going to use purple for mine, all of my work. This is what we mean by the existence of a hole, right there. Okay. So, same exact problem. All I did is just move it up a little bit. So here's where we're canceling. So here's the hole. Once you identify something as a hole, two things happen. Number one, it's no longer an x-intercept, and it's no longer a 0. That's the same thing. It's no longer an x-intercept or a 0, and it's no longer a vertical asymptote. That's what I meant to say. Sorry. Okay? This clearly identifies these pieces as being a hole, which means I'm only left with one x-intercept and one vertical asymptote. Okay? So now let's go through the list. What is my vertical asymptote? X equals 3. There's only one. Okay, now let's go to HA. Horizontal asymptote. Star. This is going to be based on the original. So what is the degree of the top? Degree 2. What's the degree of the bottom? 2. So now I have to go to my leading coefficient test. If you look at the original problem before we factored it, don't you have a 1x squared over 1x squared? So y is equal to 1 over 1. Y is equal to 1 over 1, or just y is equal to 1, is going to be your horizontal asymptote. The ratio of the coefficients in general form. That's the original form. It's not this, what's left over. Don't use the factored form to determine horizontal asymptotes. How about zeros? My 0 is only what? 1, which comes from here. All right, I believe in your list the next one you have is a hole, correct? Okay, so I have a hole at -2. Okay, the hole is at -2. Set this equal to 0. But now, I'm going to keep writing in purple, so pay attention. I'm going to do this over here. Okay? What I want to do is now I want to cancel out these, and I want to plug in -2 minus 1 over -2 minus 3. What do I get? What's the numerator? -3 over -5, which gives me what? 3 over 5? Yes? This should be in your notes so that you can refer back to it and say, why did I write this in my notes? The reason we're writing it in our notes is because we have a hole, and it is specifically located at -2 3/5. So when we get to graphing, you're going to see that if I go to my xy axis, and I go to -2 3/5, which is somewhere here, I literally have an open hole in the graph at -2 1, 2, up 3/5. There is an actual big hole. Does anyone have a question how I got the 3/5? What I did mathematically to get it? I plugged in the -2 into the remaining parts of the factored form to find the exact location. All right, now, we said we had a vertical asymptote at 3. Okay? 1, 2, 3. So take a look. I'm going to draw that in here. What you need to understand about what I just graphed is that there are 2 breaks in the graph. There's one at the hole, and then there's also one at the vertical asymptote. Which means when I calculate my domain, so down here I can do my domain, I need to think about the fact that the hole does exist. So my domain is going to be all of this in the bottom. What are the values that x can never take on? -2 and 3. So my domain is -infinity to -2, -2 to 3, 3 to infinity. 3 separate regions separated by the breaks in the graph. 1 break at the hole, 1 break at the vertical asymptote. One last thing to note, I'm verbally going to say it, we'll talk about it again tomorrow. In your calculator, if there is a hole, it will show as an error in the table. Your calculator will also show vertical asymptotes as errors. Okay, so it's never going to show you at -2 as being defined. It will say error there. All right, that's that connection to the graphing piece, which we'll talk more about. All right, you have the next assignment on your sheet for tomorrow.